Hey everyone. Up next, we have a talk from Douglas Moore on Lakehouse, the best start to your graph data and analytics journey.
Oh, sorry about that. This is the story of Quinn, the adventurer. Quinn is a data scientist living in New York City. Quinn is experienced in natural language processing, classification, regression, problems, and familiar with working with large volumes of data using distributed compute. Quinn is bright, hardworking, determined, and an imaginative problem solver. She's also a vivid dreamer. This is Quinn's story of her journey, really a hero's journey into graph analytics. One day, Quinn receives a Slack message from her boss, Miranda Jameson. Miranda has a new data set. Well, actually, Miranda says the CEO called her late on Friday afternoon from The View with this great idea. The Views is on top of the Marriott. Refreshments available. Miranda goes on, I think this data may supplement our brain research, help our people better reason about drug discovery and drug interactions. It's expansive. Billions of these things they call triples. Actually, this data set was authored by hundreds of people. Miranda asked Quinn, what can you do with this data? Quinn is hesitant to pursue this breakthrough, as it would require her to leave the comfortable life of working with structured data, grinding away on hypertuning for this new thing. Well, new thing to her, anyways. This graph structured data. Embark on this journey to analyze Miranda's graph data. Miranda introduces Douglas. They work together while in Hartford, Connecticut. Douglas, a wise and old data architect, part-time rock climber, who recognizes the potential Quinn and her research into graph analytics. Douglas encourages her to take the leap across the chasm. Douglas provides Quinn with advice and training, including advising Quinn to choose between a graph database to start her journey or to start her journey on the Lakehouse platform. First, map out each step in your journey. How else will you know if you're going to end up in a dead end? Understand what each step in your journey is and entails and requires. Secondly, what paths are narrow? What paths are wide? Where will you need compute, I/O, storage? Do you have the right amount of compute and the right kind of compute for the task at hand? Thirdly, does your team have the right skills? 90% of the graph analytics journey is the same as your other AI projects. Data, data, data. Finally, Quinn, feel comfortable that other life science companies have gone down this path in using Spark and the Lakehouse architecture to handle the complexity and the volume of the data that you face. Quinn sits down to map her coming journey. She considers what data she has to work with, the size of it, the shape of it, how fast it comes in, and how fast it needs to leave, where the data is coming from, and where it's going. She scales the area in her map based on relative CPU and I/O consumption. The journey starts with the gathering or acquiring the data for the graph. We must capture data from source systems, data warehouses, databases, files, document stores, APIs, message brokers, and the like. Next, we will curate this mountain of data. We parse documents. We run NLP algorithms to extract entities and relationships. We map relational data to ontologies. We standardize and normalize, deduplicate, and assign identifiers. Next, we are ready to structure data into a canonical graph, either a set of RDFs or a label property graph expressed as node and edge lists. We enable users to visualize and explore the graph to get a sense of what it's about. Next, users want to query the graph and characterize it with strategic queries, or begin powering semantic data layer and working on BI use cases. We need to establish a path to serve APIs, to enhance search, to build applications, especially important with the advent of large language models and LangChain, an important need for business context in those types of models. To gain full value of the graph, we need to establish a large area to power graph algorithms and graph machine learning. These areas are large because they consume vast amounts of CPU, GPU, and I/O when needed. Quinn is introduced to her new intern, Alexander, a nationally recognized mathlete from RPI. In the God of War game, he is known as Alexander the Destroyer. Alex is well versed in eigenvalues and eigenfunctions. He prefers the eigenfunctions. Quinn discusses the work ahead with Alex. She shows Alex the map. Quinn says that her boss, Miranda, the boss, using simple pattern matching, said they should look into graph databases because, after all, the data is shaped like a graph. Alex, in reviewing the map, I see this mountain of data we have to curate. Are we supposed to do that in a graph database? How will we fit documents into it, structured data? How well does it perform deduplication and entity resolution? My algorithms class tells me this is potentially very expensive, compute-wise. Alex goes on, after we curate, I see we structure the data as a canonical graph model. Then we visualize it. Oh God, yes, I just love playing with those hairballs. I know one graph visualization tool, though. It performs just like my video games. Okay, then we branch into strategic queries and tactical queries, BI and API serving, building machine learning models, and whole graph algorithms. Alex then asks, do graph databases do ML and deep learning? Quinn, you're right. Databases don't do deep learning, though they might extract features. Alex goes on. So we load this mountain of data into a database, extract features, then pull the features out to run ML on the Lakehouse. Does that make sense? Could all this be done directly? Sounds like a hefty tax to pay to move that data into the database, run the features, and then pull those features back out. Seems like we are ending up paying this data tax going in and a data tax coming out. Quinn faces additional challenges, trials and tests. She faces enemies, simple pattern matching, fear, uncertainty, and doubt. These people wear titles such as Architecture Review Board, Cloud Ops, Platform Team, FinOps, and so on. Miranda is reviewing the map and comments. Quinn, you are bright and technical. This map demonstrates strategic thinking. I feel you're encountering resistance because you haven't yet connected the architecture's capabilities to strategic business value. Connect to value that our business stakeholders can understand, and this will make your journey much easier. Healthcare expenditures now exceed $1 trillion per year in the US, so that more than $100 billion may be lost in fraud, waste, and abuse annually. Healthcare fraud also undermines both the cost and quality of healthcare provided to patients, per a Justice Department January 21, 2020 report. In another report, Deloitte details growing R&D expenses that biopharmas often blame for sky-high list prices. Deloitte found that the average cost of developing a new drug among the top 20 global biopharmas exceeded or was about $2.3 billion. In one paper published by the NIH, drug repurposing was enhanced by CNN-type technologies on the molecular graph. Quinn reaches a critical point in her journey where she realizes the limitation of the graph database are hindering her breakthrough in graph analytics. Douglas advises Quinn that the Lakehouse will serve her better with transforming raw data, running NLP, curating data, generating those triples, and creating her canonical graph model necessary for running algorithms and machine learning. Quinn must choose whether to start with the graph database, conventional wisdom, say she should use, and accept the limitation, or start her journey with the Lakehouse architecture and go the path many organizations have come back around to using. Douglas goes on to say, Quinn, consider, on the one hand, like the narrow path as shown over here. Most graph databases, like all databases, the path to loading a graph database, like most databases, is a narrow one. Databases are limited or fixed in network I/O, CPU, and storage I/O. Some databases take full day to load, or they're grossly over-provisioned and racking up costs when you're not loading and when they're idle. However, a graph database is optimized for graphy things, running traversals, performing individual point updates, doing point queries, and running high concurrency set of queries, serving APIs and applications. A graph database is decked out in specialized tools. It actually sounds like a nice place to live. They're great if you're hosting API parties. They're really fast at that. But when we need to move and process mountains of data or run algorithms that need lots of CPU cores or run machine learning and hyper-tuning or running deep learning on GPUs, which databases don't support? How many databases can run an LLM, for example? Think how long it would tie up a graph database if you ran hyperparameter tuning on your model. The Lakehouse architecture helps you in these cases. Quinn decides to move forward with the Lakehouse platform. Miranda's data is on the cloud storage anyways. The Lakehouse provides notebooks and workflows and expandable compute to run NLP, necessary to understand the doctor's notes and the research papers. The Lakehouse is currently processing the ETL and SQL for regular BI analytics in the commercial group. The nice thing about the Lakehouse is it also does real streaming. The icing on top is that Databricks Lakehouse will govern and serve the graph ML models that Quinn intends to build and deploy to production. Quinn, having journeyed before her management, the hordes of IT, prompted by questions from her intern, consulting with Douglas, her mentor, Quinn refines the map to production. Now the map shows the lakehouse next to the cloud lake of data. The expandable compute infrastructure, the ability to orchestrate her workflows, and the ability to govern the sensitive data. Quinn chooses to start with the lakehouse architecture and partner with Databricks. Quinn can get basic graph visuals with open source PyViz and video game-like type graph exploration with graph history, without standing up or managing a separate database. Databricks is well known for its ability to handle ETL and run Spark NLP pipelines, powered by John Snow Labs. They have pre-trained models that handle large-scale document processing with ease. Databricks powers through strategic queries, graph algorithms, graph machine learning, because it's enabled with the scalable compute resources. You can choose GPUs. Just 1 week into her project, and testing with the first data set shows great promise in ticking the boxes off. The approvals are in. The go-ahead towards full production build. Quinn achieves her breakthrough in graph analytics, discovering new and exciting possibilities, what she thought was possible with ordinary graph database. Quinn faces new challenges and obstacles in the road to production, but with the help of specialists, her mentor Douglas, solution architects, Quinn overcomes the hurdles and continues her journey to production. Uh-oh. Quinn receives a Slack message from Miranda, the boss. Quinn faces a final challenge, a crisis that threatens to discredit her breakthrough. Miranda Jameson demands that 2 more requirements must be met in the coming budget cycle. First, the knowledge graph needs to answer high-volume questions from our research network. Most users know nothing about Sparkle and graphs and graph queries. The board heard of our success, and with the excitement and concerns around GPT, we need to build a QA bot. However, InfoSec won't approve the use of GPT because we can't let the billions in research data leave our corporate network. Quinn smiles wryly. Quinn anticipated the need for low latency API serving, graph ML, and BI requirements. Quinn adds Stardog for the semantic layer and BI serving. The popular Neo4j is put in place for API serving. Its abilities to do low latency tactical graph queries and high concurrency operations is favored there. Databricks' built-in model serving capability provides for near real-time model serving endpoints for graph-enhanced ML models. Unsurprisingly, LLMs have also taken over the conversation too. Quinn's data architecture has that handled. The LLM can be trained in part on the curated data in the knowledge graph. The training of these LLM models, enhancement of that, can be all done for less than the cost of a decent cocktail in New York City. At the sprint demo, Quinn brings in her teammate, Ajmal Aziz, to describe the story behind his blog and soon-to-be solution accelerator. Why don't you come on up, Ajmal? Look, hey, everyone, welcome Ajmal. Brilliant solution architect, developer of this demo.
Hi, everyone. I'm not sure if I'm Alex or Quinn, but here we go. This project arose from my thesis over at Cambridge, where we were looking at experimenting with graph neural networks, which are essentially just machine learning models applied to graph structured data. The problem that we were addressing was supply chains globally form essentially like complex networks. And companies want to be able to have visibility over like this overall network that they participate in, because it essentially can mask a lot of like reputational risk, production risk, as well as like other risks as well. And so what we did was we essentially built this graph, applied these complicated machine learning algorithms on top of this graph to identify hidden links across this network. Because once you have like a complete representation of this graph, then what you can do is perform inference on that graph to actually see what your overall risk profile looks like, and you can also marry up like your other data sets to that as well. So what this blog does is it actually does that end-to-end all on Databricks. So what you can do is you can load in your graph data, you can perform a bit of ETL where you like essentially look at the natural language that accompanies your like raw text data that you have from the internet that forms this graph network, and then do name entity recognition to build the overall graph. So once you load everything in, you're actually able to marry that with your other structured data sets that you have. And the structured data sets come from like your finance and supply teams because, you know, finance always has like country risk premiums as an example of like how they quantify risk. And then what you can do is you can actually refine your overall base network by using a graph neural network that learns from the structural information that your overall network has to be able to infer hidden links. And so we were able to do all of this with MLflow. We were able to build the graph neural network, deploy it, and actually perform inference on it all within the same platform. And then the output of this is a dashboard that an executive can do that just gives them like a control level overview so that they can see, hey, like this is what my overall risk profile looks like, this is what my exposure is, and here's what my supply chain looks like almost in real time. So this is what the dashboard looks like. You can see where you sit globally, what your footprint is, and which countries you essentially like implicitly do business with that you may not necessarily see from your immediate suppliers. Yeah.
Very good. Let's walk you through a little bit of this. This is the data engineering piece of the demo. Almost all of our accelerators have a set up basic functions and install libraries and such, collect parameters. In this example, we collect the catalog name, database name, and file store path that we're going to be using. We bring down the data, if you will. We do some streaming ingest. This is an incremental ingest so that you know, if new data is added, it will be ingested incrementally. This is done with what we call autoloader. And then there's a quick browsing of the data. We pull in more data from finance. Again, more data exploration, just make sure that we understand what we're pulling in. And then some quick data engineering. You want to explain this graph? I don't.
Yeah, so the base data set essentially is looking at internet articles. And internet articles, like companies will typically publish that like, hey, I'm Shell and I just started doing business with this company, and it'll be like publicized a little bit on like whichever company's website. But there is an inherent like probability associated to that because you're using ML models to be able to infer which companies are doing business with each other and that there's a linkage there. And so the base data set has these probabilities. This is just essentially plotting what the probability distribution looks like, because when you're doing training for graph neural networks, you want to make sure that you have data that is relatively high probability, because that'll inform the training process. And so this is us just showing that there is a spread of like relatively high probability and some low probability ones that we probably want to filter out.
Thank you. CleanCo?
CleanCo is used because companies will have multiple different subsidiaries. They'll have LLCs, they'll have limiteds, proprietary limiteds. One of the companies we were dealing with had like 30 different subsidiaries and different ways that they spell their name. So CleanCo is essentially just an open source library that tracks this a little bit for you, so that if you want to have like LLC and LTD, you can just reduce it back to the base name. It's a really simple call to cleanco.basename to get that.
Very nice. And then all this is packaged as a user-defined function, so it can then run at scale.
Yep.
Okay, very good. And then we go on to training the GNN. Ajmal is an expert in graph neural networks.
So with training, what you want to be able to do is, like, there are typical elements for training like normal supervised learning algorithms. You want to have a training set and a testing set. we have to essentially take ideas from that and apply that to the graph domain, right? And so what we do is we actually sample edges from the overall graph. And so you need to create a positive graph, which are edges that you know definitely do exist. And then you need to create fake edges by negatively sampling from the actual graph. And then what you want your neural network to be able to do is predict high probabilities for your training graphs that are actually like links that exist, and low probabilities for the negative graph. And that actually informs your training process. And all of this is done after this as well, yeah. So we used a library called DGL. DGL is called a Deep Graph Library. Oh, there it is. And essentially, you have to create graph objects with DGL, and then DGL accommodates for the training process. And it uses PyTorch. It also integrates with TensorFlow as well as MXNet. But the thing that you'll note here is this can be a knowledge graph. It doesn't necessarily need to be like a singular graph that I have here. I just wanted to do it for simplicity. And the interesting part is that there is no graph database. Essentially, it's just...
Wait a second. Are you telling me no graph databases were harmed in the making of this?
None harmed at all.
All right.
And you can also query the graph here as well. And this scales like really nicely. It has really good scaling properties. So you can actually partition the graph using this as well if you need to.
Very nice.
And this is us essentially just creating our training set, validation set, and testing set for the overall graph. Now, if you've trained deep learning models before, you want to create data loaders so that when you're doing like batches of training and backpropagation, it just helps with being able to like make the training process a little bit simpler. So we had to create data loaders not for data points anymore or images, which you typically do in like typical deep learning domains. We had to create data loaders for edges. And again, DGL is heavily utilized for this as well. And then finally, we define our overall graph neural network. So the graph neural network essentially takes in inputs, which is, hey, these are two nodes or two companies. Do you think that these two should be connected or not? And there are graph layers that do this. There is an embedding layer at the final output. And the final neural network that we have is just a normal multilinear perceptron that says, here are the two embeddings for the two nodes that you're interested in. And it outputs a probability score that says, I think that these two nodes do business together or they don't do business together. And obviously, that's assuming that the network has been trained. And what I described for you just then is a forward pass through this network. Again, all done just, with PyTorch at the back end, and all the training and everything is done here as well. The last bit that's utilized is actually the training, which should be closer to the bottom, which allows you to do distributed hyperparameter tuning over graph neural networks. And you can't really do that on like a graph database because I don't know how that would conceptually work. But because you have Spark available to you, you can do essentially hyperparameter tuning or Bayesian optimization through the overall structure of the neural network, all within a few calls to hyperopt.
Yeah. That was all the setup, and then this runs it. This spawned off 20 trials, right?
Yeah.
And then all these trials were recorded in MLflow.
Correct.
So we can go back and look at those.
Exactly. And you have a model registry, and it's all there for you so that you can see what your hyperparameters look like.
And we'll see that in a second.
And you can also leverage GPU resources for this as well, which allows for training to be significantly faster as well.
And then in the final model, that's also logged
Correct.
to MLflow and registered.
Yes.
And I updated it to register it with Unit Catalog.
And now you can govern it as well.
As Carol demonstrated this morning at the keynote.
Now there's a lot of code for this, but the final bit is essentially just a graph neural network that you've trained in one notebook, and it's ready to be deployed.
Yeah. Very good.
I'll explain this chart if anyone's interested. But when you're doing like math with embeddings, you typically want to see like a structure that's useful. The structure that we saw essentially created two big groups. And you can actually infer that there is structure here that's been actually learned by the neural network. And it's not essentially just like a random chart that's been spat out. So things that are closer together probably have high probabilities when you do a dot product. Things that are further apart probably don't do business together. So there's like some learned embeddings here. And a TS, I think, is a good way to visualize that.
And so this deploys the model, right? This is a registered model. Create a UDF from that model, basically a Python user-defined function, and then perform batch inferencing on this. So you get an update of data, you can inference that.
And that's it. So essentially, once you have new companies that you run your data scraping process again to get more company information, you can just deploy this on the incremental data. So essentially, you can serve it like an API.
Mm-hmm. And so we're updating gold tables, which then power the dashboards.
Correct.
Such as this. And here's the live dashboard. Can be refreshed. And various aspects of the analytics on that. This is the index of dashboards. One thing I did want to show is this is the Data Explorer powered by Unit Catalog. And shown here in one view under my catalog are the tables related to this solution accelerator, a volume that will be used for downloading that raw data. Again, the volume will be governed. And then the registered model. And over here, we can see on the right-hand side, we can see that this version 1 has an alias called production. So when we spin up a model endpoint by clicking on this, or from that batch loading of the model for batch inferencing, we give it a tag at production. And this version of the model is used. As Carol showed earlier, she showed rolling back model. Again, this is governed with a similar scheme, like SQL-like grants. This unifies the governance of the model, the raw data, the tables, all under Unit Catalog. So it's a vision Databricks has been working on for the last couple of years. It's really coming together. So this is a serving endpoint. I just had to refresh that page. Basically, you click on serve this model, and you give it a name like supplier risk, and then you click create serving endpoint. You get, and what is it? 30 seconds later or so, you have a running model with a REST API endpoint that you can then send messages to and test it. And we record metrics that are being recorded. There's a inference table that was created with this endpoint. So now you can analyze that with SQL, put it on a dashboard, and see how your model's performing over time. So all this is available. I forked this for the Unit Catalog upgrade. The original link is here. I think we'll wrap up the presentation. Thank you so much, Ajmal.
Thank you.
Thanks.
I think there's questions just over there.
Oh, we're not done yet. The final story. Sorry about that. Okay, Quinn returns home to her new condo, having learned the value of taking risks, following her passion, and using her talents for greater good in graph analytics. Quinn shares her breakthrough with the world during DAIS 2024. Becoming a respected leader in her field of pharmaceutical manufacturing analytics, using a data lakehouse to further her research. This is the story of Quinn, a successful data scientist living in New York City. Now, who wants to head off to the view? Thank you.